In this video, we go over section 15.2, which goes over double integrals in polar coordinates. So typically, trying to calculate integrals can be difficult. Oftentimes, for double integrals, if the region that we're trying to integrate over is circular, then using polar coordinates is helpful in trying to compute the integral. So if you remember, polar coordinates is a change of variables where the variables x, y are replaced by r and theta. So r is the distance from the origin and theta is an angle. And the change of variables is given by the equations x equals r cosine theta and y equals r sine theta. Okay, so first we want to understand how to set up a double integral in polar coordinates. If you remember, the polar grid looks something like this, right? Where again, the variable r represents the distance from the origin. So imagine going out in these directions from the origin, and the angle theta is measured from the positive x-axis. And so if you divide the plane into a grid like this in polar coordinates, it looks something like this. And the basic idea is that if we translate from rectangular coordinates to polar coordinates, so here let's imagine a rectangular grid. So I'm trying to draw this by hand. But essentially, in a rectangular grid, the elementary rectangles that form the grid are the same size no matter where you are in the plane, whereas that's not the case for polar coordinates, right? So you can see here, when you're closer to the origin, the polar grid is pieces are smaller, whereas when you get farther away from the origin, the polar grid pieces are larger. And so because setting up an integral involves these little area elements, we have to understand how, when we switch from rectangular coordinates to polar coordinates, sort of these grid elements change. And essentially that's described by an extra factor of r, right? So in rectangular coordinates, the area element is just dx times dy, right? So basically just length times width. Dx is change in x, dy is change in y. So the area element is just dx times dy. However, when we switch to polar coordinates, we have to take into account again the fact that these grid elements get larger the farther away you get from the origin. And so it turns out that an area element in polar coordinates is now calculated as dA equals r times dr times d theta, right? So kind of like multiplying these two together, but you have to take into account the distance of the grid element from the origin, and so that's this factor of r here. Okay, so in total, to set up an integral in polar coordinates, we have sort of these conversions, right? So the change of variables here, where x equals r cosine theta, y equals r sine theta. So that's sort of the same from when you learned it in pre-calculus or Calc 1. And then there's this extra equation, x squared plus y equals r squared. It essentially comes from this and the Pythagorean theorem, but sometimes it's useful to have this extra equation on hand when we're trying to translate the function. And then finally, again, the area element for integrals in polar coordinates is r dr d theta. So this is the basic setup for a double integral in polar coordinates, right? So this expression here means that you replace x and y in the original function by this change of variables. The area element, again, is r dr d theta, and the limits of integration should be described in polar coordinates for the variables theta and r. Okay, so again, this is the setup in polar coordinates, and as usual, not to forget this extra factor of r when we set up an integral in a double integral in polar coordinates. Okay, so as mentioned previously, typically we want to use polar coordinates when the region that we're integrating over is circular. So let's take a look at some types of regions where integrating in polar coordinates is useful. So on the second page here, I described some common examples and also how to set up the variables theta and r. Right. So the first one here is just a simple disk of radius k. So a disk means a circle plus the interior region inside the circle. So that's typically what we call a disk. So the shaded region here is a disk of radius k centered at the origin. And so this is typically how we set up the limits of integration. So theta goes between 0 and 2 pi. Right? So theta equals 0 is the positive x-axis, and it goes around. So theta equals 0 is the positive x-axis, and then we go around completely one entire turn around the circle. So that goes to theta equals 2 pi. Okay, so and then here the radius extends from the origin up to k, so that's why r goes between 0 and k. Okay, so this is the disk centered at the origin, and in the case where we don't want the entire disk, but say half a disk or a quarter disk or something like that, what we need to do is just to change the range of values for the angle theta. Right, so in the case where theta goes between 0 and pi, so theta equals 0 would be the positive x-axis, pi would be the negative x-axis. So rotating around here, you get the top half of the disk. And in the third example here, where theta ranges from minus pi over 2 to pi over 2, so minus pi over 2 is the negative y-axis, positive pi over 2 is the positive y-axis. So this produces the right half of the disk. So again, if you need to take only a portion of the disk, you just change the range of values for theta as is necessary. Okay, so one other type of region, again, that's useful for polar coordinates is what's called an annulus. So an annulus is a ring-shaped region where it's basically a disk with a smaller disk that's been cut out of it. And so this type of region is called an annulus. And so the polar coordinate description for this type of region is just like this. So you're still going completely around. So that's the theta goes from 0 to 2 pi. However, the radius is in between these two circles here. So the inner radius is k1, the outer radius is k2. And so r goes between k1 and k2. And similar to before, if you need to only take a portion of the annulus, you just restrict the range of values for theta. So if theta, say, goes between 0 and pi over 2, it's the quarter annulus in the first quadrant. And in this particular example, I took the radius to go between 2 and 5. So like say this would be radius 2, and then this would be radius 5. Okay, so this gives you some examples of how to set up the variables theta and r for a few different kinds of polar regions. So with this in mind, next we're going to look at examples of how to calculate these kinds of double integrals.